Hello and welcome to our webcast. Today's topic will be selecting air distribution for schools. My name is Jim Oswegen. I'm Chief Engineer at Titus, and I'll be presenting today's program. I'll be joined later by David Pick, the Director of Technology, and Jonas Rosenberg, the Product Manager. As a panel, we will answer any questions you may have. There are several factors influencing the type of air distribution system selected for school applications. Local climate conditions, including outdoor temperature and humidity factors. The quality of outdoor air required for ventilation. What are the requirements for filtration and temperature control of this outdoor air? A cost-benefit analysis may indicate that one given type of system is the way to go. On the other hand, budget constraints may determine what type of system is necessary. For systems with new technology, are the required resources available to install, service, and maintain the equipment? Our focus for today's webinar will be on designs that address the thermal comfort requirements, the ventilation requirements, and the acoustic concerns for schools. This webinar will cover the thermal comfort, ventilation, and acoustic design elements required for a traditional fully mixed air distribution system where comfort air is supplied through grills and diffusers mounted in the ceiling or areas outside the occupied zone. Also, fully stratified systems such as thermal displacement ventilation, and partially mixed air distribution, such as underfloor air distribution systems. Finally, we will explore new technology by looking at a hybrid system using a dedicated outdoor air system for ventilation and latent load requirements, combined with hydronics to handle the sensible load. There are other systems such as unit ventilators that will not be discussed in today's presentation. The prevalent codes and standards used for school design in the U.S. market today are CHPS, which is an acronym for Collaborative for High Performance Schools, called CHIPS in the rest of this webinar. It began in California in 1999 and has been since updated and adopted by many additional states and school districts across the country. LEED, which initiated a specific rating program for schools in 2009. ASHRAE Standard 55 for thermal comfort and Standard 62.1 for ventilation effectiveness are referenced as benchmarks for both of the above documents. American National Standards Institute, also called ANSI, Standard S-12.60 defines the goals for acoustics. Figure 5.2.1.1 from ASHRAE Standard 55 illustrates the acceptable range of operative temperatures required for comfort. The chart is based on a metabolic activity level of 1 to 1.3. which represents an occupant that is sedentary or slightly active. The red parallelogram graphs the comfort region for people wearing winter attire, and the blue parallelogram illustrates the comfort zone for summer attire. The CHIPS recommended humidity level in the space is 20 to 60%. ASHRAE Standard 55 also recommends that for good thermal comfort, the temperature difference between the ankle and neck level of a standing person should not exceed 5.4 degrees Fahrenheit. For a seated occupant, the temperature difference should be no more than 3.6 degrees Fahrenheit. This equates to about 1 degree Fahrenheit per foot of rise throughout the occupied area. ASHRAE Standard 62.1 covers ventilation for acceptable indoor air quality. For school classrooms, Table 1 prescribes 120 CFM ventilation air per 1,000 square foot of space. Add to that 10 CFM per person. When the occupancy rate is not known, the default occupancy is 25 people per 1,000 square feet, or an additional 250 CFM of ventilation air. Table 6-2 identifies the adjustment factor for getting the ventilation air into the breathing zone of the space. Based on a fully mixed cooling with an EZ of 1.0, the ventilation air requirement is still 370 CFM. Displacement ventilation gets extra credit. So, when 370 CFM is divided by EZ 1.2, the result is 309 CFM for displacement ventilation. The results of ASHRAE Research Project RP 1373 has allowed for a change in EZ per Addenda A of the 2010 standard. For underfloor systems, when the plume of air from an access floor outlet is less than 4.5 feet above the finished floor, at 50 feet per minute terminal velocity, the EZ is now 1.2 or 309 CFM, the same as displacement ventilation. For jets with throw higher than 4.5 feet, the EZ is still 1.0 or 370 CFM is still required. There are many methods used to evaluate and specify sound requirements. ASHRAE Applications Handbook says that dBA is a weighted average that can be used to determine loudness, most typically used for outdoor noise requirements. NC is typically used to quantify sound for HVAC components to identify loudness and speech interference in the 63 to 8,000 Hz frequency range. RC identifies loudness and also identifies the sound quality as being either N for neutral, H for hissy, which is high frequency noise, R for rumbly or low frequency noise. RC can be used to quantify sound loudness and sound quality for multiple sources in a room. ANSI Standard S-1260 recommends a background noise level for classrooms of no more than 35 dBA. There is no direct correlation between dBA to NC or RC, but most sources show for comparing devices with mid-frequency range sound, 35 dBA is equal to NC and RC loudness of approximately 25. Let's examine the leading sources for guidance for high-quality designs for schools. CHIPS recommends a design which meets or exceeds the thermal comfort requirements for ASHRAE Standard 55, the ventilation IAQ requirements for ASHRAE Standard 62.1, the recommended acoustic requirements for classrooms is 45 dBA, with extra credit for 40 dBA, and the ultimate goal of reaching the ANSI recommendations for 35 dBA. CHIP's goal for selecting air outlets for fully mixed system design is 4 diffusers at a maximum of 700 feet per minute in the neck velocity and a catalog rating NC of 18 to 20. This will allow for some additional noise created by multiple sources and field inlet conditions, with room results in the NC 25 to 30 level. Displacement and underfloor systems usually result in low NC levels of 30 or less to the space. LEED certification for school requires IEQ Prerequisite 1 states to meet ASHRAE Standard 62.1, Sections 4 through 7, which include IAQ ventilation rates in Section 6. IEQ Prerequisite 3 requires a minimum background noise level for HVAC systems in classroom of 45 dBA. IEQ Credit 2 gives an extra point for increasing the ventilation air to the space by 30% over the Section 6 requirements. IEQ Credit 7.1 allows 1 point for meeting the design requirements for thermal comfort per ASHRAE Standard 55. IEQ Credit 7.2 gives an extra point by showing continued comfort in the space with a survey of occupants 6 to 18 months later. IEQ Credit 9 gives an extra point for achieving background noise levels for HVAC systems of 40 dBA. This chart from ASHRAE Fundamentals and Application Handbook chapters on room air distribution illustrates the temperature stratification profile typical for conditioned spaces. A fully mixed system such as a ceiling or high sidewall mounted outlet will mix the entire space so that the temperature measurements during cooling conditions will be consistent from the ankle region up to near the ceiling or the return air intake. A partially mixed system, such as an underfloor system, where air is introduced through the floor from the plenum below, will mix the lower occupied area and stratify the upper zone. As illustrated, the height of the mixed area may vary depending on the height of the conditioned plume. A fully stratified system such as thermal displacement ventilation will discharge air horizontally from a floor-mounted or low sidewall outlet into the space. This low-velocity jet will crawl across the floor and stratify when it reaches a source of heat, such as a person or a warm piece of equipment in the space. For these spaces, it is typical for stratification to occur proportionally from just above the floor to the height of the return. The design goal for fully stratified systems includes controlling the stratification at a rate of about 1 degree Fahrenheit per foot of rise. This will meet the temperature stratification requirements found in ASHRAE Standard 55. Conventional overhead systems provide comfort through room air mixing. For this reason, these systems are also known as fully mixed systems. In a typical application, 55-degree air is supplied from ceiling diffusers or high sidewall grills. The mixing is created by outlet discharge jets resulting in room air motion. This so-called secondary air motion is due to the entrainment of room air into the supply jet where mixing occurs. Ideally, an overhead system results in fully mixed air throughout the space with minimal temperature stratification. With a fully mixed system, the first thing the supply air does is pick up heat from overhead lighting. This is the reason why we typically need a 20-degree differential temperature on the supply air. A disadvantage of fully mixed systems is that lightweight contaminants will continue to swirl around in the occupied space. A good example for schools is the contamination from an uncovered sneeze being carried from one occupant to another. There is a wide variety of products to choose from to match the user's requirements. While architects desire pleasing aesthetics, engineers demand performance, and contractors are concerned with cost, the products shown here are popular because they are superior at providing the solution for multiple users. For fully mixed air systems, Air Distribution Performance Index, also known as ADPI, was developed by ASHRAE in the 1960s to relate temperatures and velocities in the occupied zone to occupant satisfaction. Temperature and velocities taken in the occupied zone are used to calculate the effective draft temperature points and plotted on the chart shown. The number of points inside the parallelogram divided by the number of total points tested determines the ADPI. While the goal is 80% or more, there is no direct correlation to ADPI and the percent of satisfied occupants. An acceptable ADPI does not guarantee comfort for standard 55 because it does not include factors such as humidity or, in the space, the clothing or activity levels of the occupant. It does ensure a well-mixed room which meets the ASHRAE required stratification levels. The dashed line through the center of the parallelogram also shows a relationship between temperature and velocity of about 15 feet per minute per degree Fahrenheit. So each 1 degree rise in ambient temperature can be offset by adding 15 feet per minute to the room air motion. Based on CHIPS requirements, I have calculated the range of CFM for each of the outlets shown where ADPI is above 80 and the NC is less than 20. For each of the outlet styles, I selected a 10-inch inlet at 380 CFM or 700 feet per minute neck velocity. The modular core is with a 10 by 10 neck for comparison. The results are shown in this table. I assumed a space load of 22 BTUs per square foot or 1 CFM per square foot with a 20-degree cooling. The plaque face at design CFM is NC15 and ADPI of 85. The unit will turn down to a minimum CFM of 100 and maintain an ADPI of 80 or greater. The stamp face is comparable with an NC of 18, an ADPI of 85, and a turn down to 100 CFM. The modular core is a bit noisier at NC 19, perhaps 20 with a 10-inch round adapter, but excels with an ADPI of 89. The minimum CFM turn down is 120 CFM. The louver face does well at NC 20 and an ADPI of 88, but is less flexible with a minimum turn down of 180 CFM. For cooling and heating a perimeter space with a linear slot diffuser set for 50% of the air across the ceiling for cooling and 50% down the glass for heating, ASHRAE 62.1 says that the throw to 150 feet per minute must reach the 4.5 foot level above the floor. This helps to ensure that ASHRAE standard 55 requirement for maximum temperature gradient from ankle level to neck level will be less than 5.4 degrees. To maintain an EZ value of 1.0, the maximum temperature difference from supply to room must be 15 degrees. If higher, the EZ is 0.8, which means supplying an additional 25% ventilation air during the heating season. While an auto changeover solution does not change the throw to 150 feet per minute or the 15-degree temperature requirement, the comfort in the occupied space during the heating can be improved with this option. All the warm air goes down the glass during the heating, or all the cool air goes across the ceiling during the cooling. This smoke video shows the change from horizontal air pattern to vertical occurs when the supply air temperature reaches a designated level. When the change occurs, the pattern is converted quickly to minimize the effects of drafts in the occupied zone. During heating, the air blows back toward the glass at approximately 15 degrees so the unit can be mounted into the room at a distance of about 18 to 24 inches. In addition to comfort, this system reduces energy costs as all the warm air is effectively discharged down the glass during heating. Another factor affecting sound from a ceiling diffuser is the inlet conditions of the supply air connection. ASHRAE Standard 70 prescribes the method of test used by manufacturers for air inlets and air outlets. For sound testing, the standard requires a minimum of 3 diameter equivalents of straight duct with a flow straightener to ensure that non-turbulent airstream fills the duct at the entrance of the test device. Since these ideal conditions vary for most field applications, we will look at the impact of common field installations on the room NC. This chart shows a broad summary of the research project RP 1335 conducted at the University of Nevada, Las Vegas. The transaction was presented to ASHRAE in Chicago. Multiple types of outlets from 3 manufacturers were tested per ASHRAE Standard 70, plus with a hard duct and a flex duct at 3 diameter equivalents, 1.5 diameter equivalents, and 0 diameter equivalents, and fed with a 90-degree elbow at that height. All combinations were tested with and without an opposed blade damper at the diffuser inlet. The damper was in a wide open position. Under laboratory conditions, adding a damper added up to 5 NC. With 3 diameters of straight duct, the sound was just slightly higher than laboratory or catalog conditions. At 1.5 diameter equivalents, the sound increased by 2 to 4 NC, plus another 5 when the damper was installed in the inlet. With a hard 90-degree elbow on the diffuser, the NC increase to the catalog was 5 to 10, but the damper did not create any additional noise. There is a large variety of displacement ventilation outlets to choose from in meeting the architectural and performance requirements. A disadvantage is that they are mounted at the floor and take up a great deal of floor and/or wall space. The advantages do outweigh the negatives. Displacement ventilation outlets operate at very low pressure losses, typically less than 0.04 inches of static pressure at maximum airflow. This is lower than comparable mixed air outlets. As we discussed earlier, ASHRAE 62.1 recognizes the fact that ventilation air reaches the occupant with ease and has an EZ factor of 1.2. This allows using 17% less ventilation air, or giving you a head start toward the 30% required for the extra lead point. At maximum airflow, most displacement ventilation outlets are less than NC25. Another advantage, especially in schools, is contaminant control. Since the supply air travels across the floor, then stratifies to carry lightweight contaminants to the ceiling-mounted return inlet, contaminants do not swirl around the occupied zone, but are carried upward to the return. With displacement ventilation, outlet cool air is discharged into the space at less than 100 feet per minute, usually less than 80 feet per minute. Cool air falls to the floor and continues to travel across the floor until it reaches a heat source and stratifies. Air velocities above 50 feet per minute are usually considered to be the adjacent zone and clear of permanent occupants. The adjacent zone is identified by the dark area on the illustration shown. Typically, comfort conditioning is provided to the space until the velocity falls below 15 feet per minute. This usually means that the comfort area extends 5 to 6 times the distance of the adjacent zone. In order for displacement to work most efficiently, the return air should be pulled from well above the occupied zone, preferably from the highest point in the room. Since much of the heat load from the overhead lighting is captured from above the occupied zone, the supply air temperatures are higher. You should expect higher return air temperatures than would be found in a conventional mixed air system. Humidity issues. In order to avoid potential humidity issues and air quality concerns, we need to limit the humidity to 60% or less. There are many strategies that we can employ at the air handler, or we might choose desiccant dehumidification. If we choose to drop our air temperatures to 55 degrees to wring out the moisture, we can blend the return air with the supply and bring it back up to 65 degrees. Because by design, displacement ventilation works on the principle that buoyancy drops cool air to the floor, it is also true that warm air rises. Thus, displacement ventilation is not effective as a heating device. Typically, heating must be handled with a separate system. One solution might be a dual-chamber diffuser. This dual-chamber diffuser is equipped with a baffle in the plenum to change the direction of supply air to direct it into the room through the displacement face on the top during cooling. During heating, the air is directed to the bottom chamber where a high-velocity jet of warm air is directed across the floor. The supply air is delivered to the outlet with one duct supplying both warm and cool air to the space. The diffuser shown on the left uses onboard technology to switch the baffle from cooling to heating position based on the temperature of the supply air. The diffuser chamber on the right directs the air to the proper chamber based on the thermostat setting for either heating or cooling. In a classroom, this is a floor plan diagram that shows how a classroom may be set up for displacement ventilation comfort control. Two diffusers at each corner of the front of the classroom will comfort condition half of the room. Underfloor air distribution systems provide enhanced individual comfort. Each occupant has direct control over their own thermal comfort. Typically, there is a diffuser located near the work area that can be manually adjusted as needed for comfort. The thermostat control from the office is no longer necessary as the office occupant has manual adjustability of the floor diffusers. Many studies have shown that the more control occupants have over their own thermal comfort, the more comfortable they will be and the more productive they will be. A major advantage of underfloor air distribution is the accessibility to service cables when a space is reconfigured. This is also known as churn. For a school application, this may be a computer lab. The products specified in core areas for underfloor projects are typically small round or rectangular outlets to be located near the occupant's work area. These diffusers have a high induction swirl airflow pattern and can be manually adjusted or actuated. The typical design point for this style of diffuser is 80 to 100 CFM with throws to 50 feet per minute limited to the 4.5 foot above the floor height. They are typically operated at plenum pressures of less than 1/10 of an inch and have low NC levels. The round swirl diffusers can be used with an actuator that is controlled by a zone thermostat. These installations are typical for common areas such as break rooms, lobbies, or large areas controlled by a single zone thermostat. For perimeter applications, while the loads in the core area remain fairly constant, loads on the perimeter change dynamically throughout the day depending on outdoor conditions. A common perimeter installation of ways of handling perimeter load is the use of fan-powered thermal units, which are ducted to rectangular diffusers that are rated at higher airflows than interior swirl diffusers. For underfloor air distribution applications, Fan terminal units are typically equipped with ECM motors for maximum energy efficiency. ECM motors can be controlled by the building management system to vary the amount of air delivered to match the load in the space. These fan-powered terminal units may also be equipped with hot water coils or electric heating coils. This is an underfloor passive perimeter system. This perimeter underfloor system operates to match the varying load conditions without employing the use of a fan-powered terminal. The passive perimeter system consists of a perimeter hot water heating section or a perimeter SCR electric heating section, and the perimeter variable air volume cooling section. This system uses a continuous run of linear bar grill that gives the system an architecturally appealing appearance along the perimeter. The system is modular so that heating or cooling units can be placed as required to match climate and zone load conditions. First, the VAV perimeter cooling system. The unit shown in the lower left-hand corner of the slide is a 4-foot-long VAV cooling supply air unit. The installation view shows the simplicity of the installation on the perimeter for this product. The product is flanged on both sides and rests on top of an angle iron on the exterior wall side. This angle iron is field installed and supplied by others. The exterior wall side flange of the grill simply rests on top of the carpet tile and then on the angle iron. On the room side, the inside flange of the product rests on top of the carpet tile as well. There are no tools required to install this product, which makes it very easy to access if needed. Once the unit is installed, the continuous length of linear bar grill mounts on top to complete the installation. When fully open at 0.07 inches of plenum pressure, this unit delivers 225 CFM to the space with a throw height of just 6 foot above the floor. As the supply air is delivered through the transverse aperture shown in this picture, the room air is induced into the supply air and mixes. This induction process and mixing keep the supply air jet from gaining momentum to create long throw. This video illustrates the unit during operation at 225 CFM, maintaining a 6-foot throw above the floor. Each one of the marks in the black background are 1 foot apart. As you count the marks, you see from the smoke that the throw settles at 6 feet. At the peak of the throw, the airflow rolls over on itself due to the tri-deflection grill and moves into the space to cool the occupants. For perimeter heating, the fin tube hot water or fin tube electric units are specified. The electric heat unit is controlled by an SCR controller. These plenums are 4 foot in length and 6 inches wide as a standard. They install in the same fashion as the VAV cooling unit previously discussed, with an angle iron on the exterior wall and carpet tile on the room side. This will allow a modular installation to match your climate requirements. How does this passive heating unit work? Cold convection currents flow down the glass. Room air is induced into the front of the unit. The mixture of air is induced into the plenum and is warmed up as it passes over the fin tube heater. Warm air rises up the glass through convection, totally independent of the cooling system as required by ASHRAE standard 90.1. This is a hybrid solution for schools. The floor-mounted active chilled beam is specifically designed for North American classroom applications since it minimizes the design issues previously stated and combines the benefits of displacement ventilation conditioning and chilled beams to address noise, humidity, and ventilation issues very effectively. and efficiently in the classroom environment, as well as offering other benefits. The classroom is ventilated and conditioned in a displacement manner identical to that in a conventional displacement system. However, the unit also incorporates a series of induction nozzles and heat transfer coil, which allows the induction and the reconditioning of room air within the terminal. This cross-sectional view shows where the dedicated outdoor air system inlet feeds a series of nozzles in an upper chamber for heat and a lower chamber for cooling. The nozzles induce room air through a perforated front panel, which can be heated as it passes through the upper coil or cooled as it passes through the lower coil. The conditioned air is distributed through an outlet on the top of the unit for heating loss on the glass and back into the lower perforated face to handle the sensible heat gains in the space. This slide illustrates the operation of the unit in the cooling mode. Primary air is delivered through the induction nozzles. The velocity of the nozzles induces room air through the integral heat transfer coil, which is then cooled in accordance with the space thermostat demands prior to mixing with the primary air. The use of room air induction and reconditioning allows the use of 100% outdoor air as a primary air source. This outdoor air is cooled to saturation at 50 to 54 degrees within the air handling unit, then ducted to the terminals. Mixing with the reconditioned room air elevates the temperature of the mixture to a level which is appropriate for displacement conditioning of the space. The space thermostat regulates the amount of induced air conditioning in accordance with room cooling requirements, resulting in a constant volume, variable temperature discharge to the classroom. Most classrooms can be adequately conditioned and dehumidified with a primary airflow delivery equal to or just slightly above the required space ventilation rate. Most applications allow the chilled water supply to be maintained at least 1 degree above the space dew point temperature so that no condensation to the terminal unit occurs. Note that the return airflow from the classroom is equal to the primary airflow rate so that the return air is exhausted and no recirculation at the air handling is necessary. As such, the recycling of airborne contaminants to the classroom served by the air handling unit does not occur. This slide illustrates the operation in a heating mode. Primary air is delivered through the nozzles, which induces room air through the upper coil, which is heated and delivered through the grill on the top to satisfy the heating conditions in the space. At the same time, the primary air delivered through the nozzles in the coil below mixes with the room air and delivers cool air to satisfy the sensible load conditions in the space. The resultant air delivery to the space is displacement type mixture of primary and recirculated at 62 to 68 degrees. This table compares the systems that we have discussed using several different factors of interest. For optimum temperature control in the space, a fully mixed system is superior. For IAQ and ventilation effectiveness, choosing displacement ventilation or underfloor may be a superior choice. For minimum sound levels, displacement ventilation and underfloor systems may be superior. For heating, displacement ventilation requires additional consideration. Fully mixed systems provide superior humidity control. Displacement ventilation and underfloor air distribution are lower operating pressure and may be lower in energy cost. Fully mixed systems generally have a lower first cost. Underfloor offers the greatest flexibility when churn is required, such as in a computer lab. Additional information can be located in the ASHRAE Fundamentals Handbook 2009, Chapter 8 for sound and Chapter 20 for air distribution. For ASHRAE Applications Handbook 2011, Chapter 47 for sound and Chapter 57 for room air distribution. Thank you for your attention. The panel will now answer your questions.